Hello and welcome to this section of using a Knime with in Cheminformatics, and this is the second series of the videos in Knime, and we'll be working on some of the pipelines I have made. First one is how to do similarity search, then how to find activity clips, and also plot heat maps, and the last one is kind of a scaffold enrichment. How can you extract scaffolds and like cluster the compounds using k-means and extract scaffolds from the cluster, and then figure out which are the important uh, cluster scaffolds in the cluster. So these are the important techniques which like kind of introductory techniques, are like the I will say the first steps of doing data analysis in cheminformatics, especially like extracting the chemical data and try to figure out the meaning of these chemicals and uh, how are they working in biological systems. So first I'll see how to perform a chemical similarity search. So this node is a Marvin sketch node. If you try to configure it, it will open a Marvin uh, this drawing chemical drawer where you can paste the compounds, the smiles, paste the smiles into this Marvin sketcher. You can do a lot of like calculations on this and of this compound here, but we'll be using this as an input molecule, and we'll be searching compounds against this input molecule. So once you draw the structure and then you just click apply. Since the I've already done, so that's why it's not taking. If you have a new structure, you can edit it, and then after that, if you have a structure file, so you need to read it. So I have a smiles structure file here, uh, and it shows it's been. I've read it here in this file, so it's there in compounds XML. So all the pipelines and the compounds are mostly like given here on the GitHub account. So you read the file, and if you want to reset it, you just reset. So I reset the node and then I calculate the fingerprints using the RT-Kit fingerprint. So it will take some time because there are like 10,000 molecules. So this is working. So it's and once until it's done, so the job of this next node is kind of queued. So once this job finishes, the table will move on to molecule to indigo. So it will convert. So this is indigo is another cheminformatics toolkit which like has a lot of functionalities, and there's also indigo node here. And also, why do we use indigo? Because it has a nice chemical visualization representation. So that's why most of the people use indigo to visualize chemicals. So once this is done, you can just see the valid molecules which pass, and these are the fingerprints, the artificial fingerprint which is calculated, and these are the chemical structures. And next we'll be performing, and this is the molecule against which we'll be searching. So we'll be generating the same fingerprints what we generate in this one. So need to configure it. Okay, I want to generate max kind of fingerprints, and also here the max against the smiles column. We'll generate the fingerprint, generate a new fingerprint column and dump the binary fingerprints there. So then I perform this. There is a similarity search node here, and it performs similarity search and try to configure what you will want to do. You need to see that okay, it's doing fingerprint on this column, and also you need to select the coefficient, the similarity, and minus distance. And if you want to use a range filter, okay, give me compounds which is like in between 0.6 and 1. So we apply it, and then it just run it. So I'm running the full stuff here. So if there is a missing value, just remove this. Remove. It will generate a table. So all the remove the rows which couldn't calculate the similarity, and then you do a column bit of column filter and remove these columns, and then these two columns, and then I convert the molecule to indigo again. Then I do a column filter of this query, and then convert the query molecule, convert this query molecule to indigo style, and then the rule engine is the rule engine actually, if you want to place your structure against the similar result, against the result you got, you just put this true equals the smiles, which is the smiles of the this single molecule, and you append it as query. So once you do that, you just need to show the structure. You need to convert it to indigo and do some column filtration, and finally you just visualize the table. So here is the final results. This is the similarity score, and this is the query molecule, and these are the results. You can just sort the tables, sort descending, and this is the top molecule, which is similar to this using the max fingerprint. So you might want to build a pipeline using the various kinds of fingerprints you want to use here, like max, and try to figure out which what type of molecules do you get while you do this kind of the similarity search. You might end up with getting different kinds of molecules using different fingerprints. So I leave this thing as an exercise for you, and just figure out what molecules come up using the different kinds of fingerprints you have seen. The next one is the Knime activity cliffs. So I read some molecules here. So the activity cliffs, there's a very nice paper by Rajesh Guha, one of the developers of this RCDK here, and they actually use this equation here to find the structure activity landscape index. They actually subtracted the modulus of the activity of the ith compound with the jth compound, and then divided by 1 minus the similarity. So you take the distance here. So and then you get the kind of solid index scores. So it is like there is possible that two very similar but not two are very similar. The two compounds are very similar but not identical. Will have like similarity value of 1. In those cases, like if you have similarity of 1, then the solid will go to kind of infinity. So if it is less here, like 0.1, so then it might then this is also different. So then there exists a structure activity landscape. So coming to the pipeline, so I don't have activity values here in this file. So you can take any QSR data set as a STF file with some activity values, and you just read it, and then you put the results here in the similarity network viewer. It will show you the SALI index. It will compute a network for you based on the similarity cutoff and also the properties. It will show you a nice table. There's a distance matrix calculator plugin which you want to put in, which calculates distance matrix here, and with the help of these final distance matrix, you put the data on this similarity network viewer and similarity viewer. This actually shows you a heat map here, a beautiful nice heat map. You can just see the network, which I have done in our last time. You can also use this tool to plot heat maps, this blue to red, and you can see the distance here. The distance is kind of 1 minus similarity, so that's why these diagonals are not ones. In a similarity matrix, this diagonal should be 1. So remember, like when you put the distance matrix, it's 1 minus similarity. So these are all you can see are 0, and this is like 0.1. So and this has a very high distance, so it means it is less similar, and this one is very kind of small small value, but it is very highly similar. So coming to the network view, let's see what does it plot. Uh, how's the network? You can change the view. So if you put on here the click, just move hover around your mouse in some of these drop bank IDs, and it will just show you. Uh, and you can change the network configurations like this, and just so once you click it, it will pop the results for you here, and also show you in a table the similarity along with the property value. So for example, the property I have taken log PS. So the similarity is not the chemical, it's the distance value. So if you see, this is distance, so it's like 0.6. But if you go down, it's 0.8 here. So it indicates that this is not a similarity value. So this is a distance value. That's one minus similarity, which has been given here. And the cliff score indicates the activity cliffs which exist here. You can read about the activity cliffs in this nice paper, which indicates it draws network. So it's basically this tool is being implemented on this Knime pipeline. So this is the activity clips. Next, we'll be doing the scaffold enrichment pipeline. So again, I have a set of structures here. You can just see I read the molecules. Here from the Dropbank database, does lots of these tags associated. So I convert the molecule into RDK tag. There's an exclamation mark here, which indicates when you point your mouse, it shows that 6 of the 1500 rows has some problems of sanitization. It couldn't convert those molecules. There were some errors. So again, I convert the molecule to RDK to Indigo for better representation. I generate the fingerprints of the RD kit here. Then so once this is a compressed form of fingerprint, I expand the fingerprints, like converting into each bit into a column-wise vector. So it will be like 1024. Then I do a column filter which keeps only the bit vectors, and then using the bit vectors, I use k-means clustering on the bit vectors to cluster the compounds based on the fingerprints. Then I group the compounds based on the number of clusters, and then I start a loop on each of the table row, and so each of the table row I start a loop, and I extract only one of the clusters which matches a pattern. So after this table, so here it generates a table in group by, and it will name it as let's see, the pipeline is, the computation is finished. So what does this column filter do here? The column filter just removes this kind of IDs, which is not required, and keeps only the bit vectors. You can see, and using the k-means, it will select only the bit vector generated columns and perform the clustering. And here I just group by using the cluster. So once the k-means is done, it appends a new column cluster, and then I configure. So there is no configuration on this. You just put the table row to variable root to start. So what happens? It extracts each row, and until the loop is finished here, it will perform these things on each of the rows. So there is a flow variable here, which is important, which actually takes the parameter from the previous node. So the flow variables you can see is the cluster. The cluster is that table name, so it will for for each row it will extract the the, the cluster pattern, and then it will generate the Markov scaffolds for that, and there's a value counter uh, represents the how many in the cluster. For example, uh, this is the last result which is computed. So for cluster 9 there are 562 compounds. So it exists. So there are 9 clusters. You can just see. So 9 clusters means there are 10 clusters. This clusters starts from 0 here. So I need 10 clusters. So and then number this one converts the table row to a variable here. And number 2 the variable means the cluster variable, and then math is a math formula, the column with the number of cluster counts, and remember there is also this expression count which counts the number of data values. So it extracts. Okay, so the variable output is for each of this for each iteration it shows these kinds of variables here, and which and this I again create a flow variable pipe here line here, and then in math formula I also count it out, and then I end up this loop. Uh, so I actually merge all the things into a single table out here. So once you just to finish it off, the final results will be like this, and you can see at the end you move, so you can see the cluster column, the molecule, and the cluster number here. So the number of compounds in the cluster. So 1, 2, 3, 4. So in cluster 0, these are the 4 compounds. Actually, this is the scaffold. This is the scaffold, which has this 4 clusters. So these varieties of scaffolds are found in cluster 0. When you move down, these are the other scaffolds which are found in this cluster, and so on. So then you can move on, and change the name of this this molecule plus this column to scaffold, and then make a column filter, remove the other columns, only keeping this cluster and the count, and convert into a nice entire picture using the Indigo toolkit. And then you remove the compounds which has missing structures or something, and finally at the end you just get the filtered molecules. So this is why I use this row filter, because what you can do is you can just configure and you can use a pattern. Say for example I want keep only the compounds which matches the cluster 0. So only 4 compounds are there, and once you do that, so it represents the 4 compounds. So it's just a filtration scheme, and if you don't want to see everything in a single table, you can just use this filtration thing. Okay, give me all clusters, say 4, and only the compounds of cluster 4, and then you execute it. Just see filter. So all these scaffolds are present in the cluster. So 3 compounds from cluster 4. I hope you understand this kind of thing, and let me know if you find any problems on this looping variable, because this is kind of advanced kind of pipeline which can uses the flow variables and everything. And we'll be giving you some of the notes on flow variables later on, because it's advanced kind of building the pipeline. So also you want to test with, so these are all the pipelines, my local pipelines here. You can go to examples and just check out the different kinds of pipelines. This is how you can learn Knime by itself. If you want to know about how to integrate R in Knime and to perform some analytics, and there's a lot of other pipelines which is available. I think it's more than 100 pipelines. So it's up to you. If you have some interest in pipelining tools, you can use Knime for this, and just check out this all these examples given here. Also, you can use the Knime community to ask questions. It's very pretty active community, and they might help you out with your queries. So you need to submit your pipeline, and they might help you out with that. Thank you. I hope you enjoyed this lecture video. Thank you.